Hello, my name is Jessica Tingley, and I'm excited to present our work on extending multi-robot assembly capabilities through a modular skill-based interface. This project was conducted during the RISC program at Carnegie Mellon University in the ARCS lab in collaboration with Philip Huang and Dr. Li. So let's dive in. Fully automating assembly has become a pretty critical goal across many industries, from consumer electronics to aerospace or logistics. And multi-robot systems are attractive because they increase throughput, spatial coverage, and allow for dexterous tasks that would be hard for a single arm. For instance, one robot might be able to stabilize a part while another performs some kind of fastening or alignment. But there's a pretty big problem. Most systems are hard-coded, and even when coordination strategies exist, they don't really generalize well. Changing domains, maybe from some Lego assembly task to furniture assembly, often means rewriting a lot of the system. And this is because we lack reusable abstractions for robot behavior, task logic, and how those interact with hardware. Symbolic planners like Planning Domain Definition Language or PDDL can specify goals, but they don't really bridge the gap to physical execution. So our goal is to address this gap through a modular, skill-based interface that can work across robots and domains without rewriting the entire planning stack. So before we dive into our approach, let's first introduce the execution and scheduling backend used to validate the performance of our proposed skill graph in multi-robot settings. So this is APEX-MR, which was developed at Carnegie Mellon University, and it's a framework for asynchronous multi-robot coordination. It uses temporal plan graphs to manage concurrent execution and has been validated in Lego assembly tasks. But APEX-MR is tightly coupled to its domain, and there's no abstraction layer for specifying skills or task semantics, and this really limits its adaptability. So our contribution is to insert a skill graph interface between symbolic plans and execution. This interface will formalize robot actions and execution conditions, and so this enables reuse, easier debugging, and easier integration with other planners and controllers. So this is the high-level skill graph architecture, and on the left, you define your task. You can see on the left the goal state, parameters, and environment, and then in the center, we have interactive functions that bridge the symbolic task definition with real-world robot execution. So this includes grounding objects, checking feasibility, and simulation. And then on the right, we have the skill graph itself, which is broken into 5 core modules. So we have physical entities like robots, objects, and environments. We have concepts, including primitive atomic skills and composite meta skills, where meta skills are composed of various atomic skills. Then we have executables, which are the actual logic that defines how to carry out skills. We have evaluation metrics, which define how we validate preconditions and postconditions. We have data structures that maintain runtime state and serve as the I/O interface. And so this modular breakdown allows the same high-level logic to be executed on different robots in different environments using different planners. So in going into a little bit more detail, each task starts with symbolic planning at the meta skill level. And then these are decomposed into atomic skills like pick, place, or align. And each atomic skill is paired with some corresponding executor. And this executor encapsulates preconditions, execution logic, and postconditions. So like I mentioned before, the modular structure allows you to swap components in and out, so you can change your robot, your task domain, or your motion planner without rewriting the entire system. And then we also have evaluation modules like condition evaluator or constraint evaluator that ensure a skill only executes if it's feasible and valid in the current context. And then finally, we have, like I mentioned before, the data structures like robot state, environment state, and skill parameter, which store runtime information and provide consistent interfaces between modules. So going into a little bit more detail here, we can look at an example of a pick and place meta skill. So as I mentioned previously, each skill follows some kind of life cycle. We have precondition evaluation to execution to post-condition checking. So we can see in figure 3 here how a meta skill like pick and place is decomposed into multiple atomic skills. So for instance, pick, place, and transit here. And each is validated with symbolic checks and then passed to a specific executor. So figure 4 here zooms in a little bit to the pick atomic skill. So we first validate conditions like, is the object visible maybe, or is the gripper ready? So these are kind of maybe depend on your domain. And we do this using a condition evaluator. Then we run the pick executor, which might call a motion planner, an inverse kinematic solver, a controller. And then once complete, the system updates the robot and environment states and continues moving on through the execution. So this pattern, as I mentioned before, enables symbolic planners to chain skills while letting the skill graph handle kind of the complexity of how those skills get executed. So more specifically for the work done this summer, we extended the skill graph framework in order to demonstrate its ability to generalize to a new task domain, and this was magnetic block assembly. You can see some examples of these magnetic blocks in figure 5 here. So our system controlled 3 robot arms, and so this third arm was also an extension to the skill graph framework, extending off of the Apex MR, which used 2 robot arms. And so blocks were placed on a grid, and they had to be picked, aligned, and pressed into place with the correct face and grip orientation. So this task introduced new parameters like press face, which described which face of the block needed to make contact with the structure, and grip orientation, which defined the end effector pose needed at that time of placement with the structure. So these domain-specific additions were encoded directly into the skill definitions and executors, but everything else, planning, scheduling, execution logic, remained completely unchanged. So this was, again, in order to demonstrate that our framework supports plug-and-play extensions to new physical domains. So here's a look at the experimental setup we use. So the environment consists of a workspace shared by 3 Canova Gen 3 robot arms, each equipped with parallel grippers. So each robot was positioned at a different side of the table, enabling spatially distributed collaboration on maybe complex assemblies. And the target structures were defined in terms of a printed tabletop grid, as you can see in figure 6. So this provided a discrete coordinate system for block placement and alignment. And then we ran both sequential and asynchronous executions using our skill graph and Apex MR integration, with MoveIt2 providing motion planning and control. And we executed this in simulation in ARVIS, as you can see in figure 7. So in this video, we can see first the sequential execution. So one robot moves, picks, and then places, and then returns home, and the next robot does not begin moving until that first robot has completed its placement task. So we can see here, we wanted to press a different face of the block with the structure. So the second robot approached the structure in the middle from a different direction than the first robot. And same with this third robot, we wanted a different face being joined with the main structure. And here we can see this is the asynchronous robot trajectories, the asynchronous robot assembly. So we can see that 2 robots start at once, and then the third comes in and finishes. So as we just saw in our experiments, we were comparing sequential execution with asynchronous execution through Apex MR. And this was in order to test that our extended framework was maintaining the expected speedups. So as you can see in this table, we saw a consistent speedup of 55 to 60%, which is what was expected, with an average speedup of 57.45%. And these were across tasks involving 3 to 5 magnetic blocks. So these gains stemmed from parallelization and reduced idle time thanks to Apex MR, but the skill graph was ensuring that tasks were executed safely and correctly, even in asynchronous settings. So the important thing here is that we didn't have to handcraft motion sequences. Everything was generated through modular skills and then validated on the fly. So there are several exciting directions moving forward. We're working on adding more collaborative skills like cooperative handover or support for the magnetic block domain. And this would allow the robot to hold an object while another attaches a new piece. And this also provides leeway for more dexterous and more complex structures to be created. We're also working on supporting subassemblies, so letting robots build parts independently and then join them together. So this would require encoding more dependencies, some physics-aware reasoning, maybe if we want to identify where the subassemblies are in a larger assembly file. And then we also need to have some kind of spatially aware transport, because if we are transporting large pieces of assembly, we need to make sure that we are generating collision-free paths. And lastly, we are looking into integrating some online replanning and perception feedback to make the system even more robust. So in conclusion, we have introduced a new domain-agnostic skill graph that generalizes symbolic task planning and execution across robots and tasks. We showed how this enables new domains like magnetic blocks with minimal changes and achieves significant speed up in asynchronous execution. So our approach bridges symbolic reasoning and physical grounding with modular abstractions, making scalable multi-robot assembly more practical, interpretable, and extensible. So finally, I just want to give a huge thank you to my amazing mentor, Philip Huang, and my PI, Dr. Lee, as well as everyone in the AI for Robotics Coordination at Scale Lab for all their guidance and support offered throughout the whole summer. And I would also like to thank the Robotics Institute and Robotics Institute Summer Scholars Program, specifically Rachel Burson and Dr. John Dolan, for making this opportunity possible. Thank you for listening.